Thank you. So now I request Dr. Rachna Chaba, the Associate Dean R&D, to hand over the bouquet to the Chief Guest, Dhar. Thank you. So now I request the Chief Guest, Professor Deepak Dhar, to officially release the annual report. I also request Professor Gauri Shankar, Professor Sudeshna Sinha, and Professor Jagdish Singh to join me. Thank you very much. So now I invite Professor Gauri Shankar, the Director of IISER Mohali, to give the welcome address and also kindly introduce the Chief Guest. Professor Gauri Shankar, please.
So, good afternoon, everyone, and it's my great pleasure to welcome all of you for the celebration of the IISER Mohali's Foundation Day today. We have just begun to emerge out of the COVID pandemic, and today is the first offline physically conducted Foundation Day after a period of 3 years. So I'm very happy that all of you are here today for this function. In the morning, there have been plenty of programs that have been held by our faculty and student volunteers during the day for school students, which have included various competitions, science demonstrations and exhibitions. And my congratulations go to all the student winners in the quiz and the competitions. Just a few minutes ago, we had the prize distribution function in another lecture hall with a very large number, approximately 800 students have visited the campus today for these celebrations. The preparation of the annual report for 2021-22, which was just released by our chief guest, Professor Deepak Dhar, has been very ably coordinated by the Dean and Associate Dean of R&D, and my grateful thanks to both of them. The annual report will be placed in Parliament in November, after which it will also be available as a public document. The report provides a record of the Institute's outstanding research achievements and publications across its 6 departments, the awards and honors that have been received by the faculty and the students, the initiatives of our Technology Business Incubator or TBI, and the efforts that we had taken to teach courses and conduct exams for the students during the pandemic period. To summarize in one sentence, we have done extremely well in the past year, and the future also looks bright. I now have great pleasure in introducing our distinguished Foundation Day speaker, Professor Deepak Dhar. Professor Deepak Dhar was born in 1951, did his MSc Physics from IIT Kanpur, and his PhD from Caltech, USA. His research career has been primarily at IISER Mumbai for almost 40 years. And for the past 6 years, he is at IISER Pune as a distinguished emeritus professor. Professor Deepak Dhar is an international authority in statistical physics with particular reference to phase transitions. And he has several outstanding discoveries and contributions to his name. He is credited with introducing the concept of spectral dimension in the studies of fractals. And along with another close friend and well-wisher of IISER Mohali, Professor Ramaswamy, he developed the Dhar Ramaswamy model as a solution for self-organized criticality of the abelian sandpile. Professor Dhar has also made fundamental contributions to the problem of directed site animals enumeration and for developing models of metastable glassy states in stochastic evolution. Not surprisingly, Professor Deepak Dhar has been the recipient of many prestigious awards and honors for his pioneering work. These include the INSA Young Scientist Medal in 1983, the Shanti Swarup Bhatnagar Prize in 1993, the Robert Schrieffer Prize of the International Center for Theoretical Physics in 1993, the S.M. Bose Medal of INSA in 2001, the TWAS Prize in 2002, and the J.C. Bose Fellowship in 2007. He is an elected fellow of all the science academies in India and also of the World Academy of Sciences. Earlier this year, the Commission of Statistical Physics of the International Union of Pure and Applied Physics awarded the prestigious Boltzmann Medal to Professor Deepak Dhar, which is a prize that was instituted in 1975. It is given once in 3 years for outstanding contributions to statistical mechanics, and Professor Dhar is the first ever Indian to be its recipient. So the Foundation Day lecture by Professor Dhar is titled 200 Years of Studies of Phase Transitions, and I would welcome him to deliver the lecture. Thank you.
Thank you, Professor Gaurishankar. So now I invite the Chief Guest, Professor Deepak Dhar, to deliver the Foundation Day lecture. I request Professor Gaurishankar, Professor Sudeshna Sinha, and Professor Jagdeep Singh to take their seats in the lecture hall.
Okay. I think this is good. Thank you very much, Professor Gaurishankar, for a very kind introduction, and I'm very happy to be here and share some thoughts with you. You know, I accepted the invitation to come here, but I wasn't very sure what I should say. And I appreciate that all the audience are not necessarily physicists. So this lecture is going to be somewhat popular science lecture and not very, very technical. But I hope that you will find it interesting and maybe it will say something of some interest. So I just start by giving the outline. So I will start with some preliminaries. Then it so happens that, you know, it is the 200th year of the studies of phase transitions, and somehow this anniversary hasn't been noticed much by other people. So I thought I will say some little bit about the original experiments which Cagniet de la Tour did in 1822. Then I will discuss the theoretical framework for describing phase transitions. On what basis do we discuss phase transitions in general in physics? I give an example of the IISER model in 2 dimensions, which is a prototypical example of phase transitions. And then there is a very nice theory of how phase transitions happen, which is called the Li-Yang theory, which I will describe qualitatively. And then there is a scaling theory of continuous transition, which is called renormalization group theory or something. So I will say a few sentences about these. And then the question is that, okay, so this is sort of what is known about phase transitions, but then there are still many open questions and things which we don't yet know, we would like to understand better, and these are discussed in number 7, which is other things we don't understand so well, and then I will summarize. Okay, so let us start with the preliminaries. So the fact that if you take water and you heat it up, it becomes steam, or you cool it up, it becomes ice, they are very familiar and well known. But if you think a little bit about them, they are still actually quite surprising that they happen like this. Because if you take ice at minus 0.01 degrees centigrade, then it is ice, and it is very nice ice, and you change the temperature by 0.02, and it becomes water, which is very, very different. Now the temperature of the ice has not changed by more than a fraction of a %, right? And so how can such a small change in temperature make such a big change in the properties of the material? Now, when I studied in 10th grade, I guess, we were told that there are these bonds between solids which break at higher temperature. That is why a solid becomes a liquid. But if you learn a little bit about kinetic theory, you realize that temperature gives the average energy of kinetic energy of molecules. Actually, at any temperature, there are many atoms which are twice the average energy, and there are many atoms which are less. So the fraction of atoms which have above the sort of stipulated energy at minus 0.01 degree centigrade is not so different from plus 0.01. And so how come that this very tiny change in the average property, not in the individual property, can make such a big difference? So it is surprising and needs some explanation. The explanation is known, but I think the fact that it remains something which is still quite amazing should be appreciated. Okay, so as I said, the scientific study of phase transition may be said to start with the experiments of Carnier de la Tour in 1822. And I was just talking with a friend, a physicist friend of mine from Scotland, and I was telling him that, look, people don't seem to know about this Carnier de la Tour experiment, or they don't mark the anniversary. And he said, who was Carnier de la Tour? Okay, so this is a good question. I think the history of science is not very, very important. But I think it's important to realize that 200 years ago, people knew so little. And then in 200 years, we have learned so much. And that point one can appreciate. Even a high school student can appreciate. Okay, so that is what I would like to emphasize a little bit. So what did Carnier de la Tour do? This is what I would like to explain first. And so what he showed was that if you take liquid and gas, this is a picture which I have, sorry, this is, here. Yes, so in this picture there is this solid, liquid, gas. This is a familiar phase diagram where you are at a fixed pressure and you change temperature, you go from solid to liquid to gas. When you heat up, first the solid melts and then it boils. But if the pressure is too high, then you go from solid to liquid, but from liquid there is no boiling further. You can keep on heating, it will remain the same, and it looks like a gas at some stage, but there is no boiling point. So this point was not appreciated before, because in our everyday experience, all the liquids tend to boil. There were some gases which didn't become liquid ever. They were called permanent gases like oxygen and nitrogen and so on and so forth. Now we realize that of course they can be made into a liquid, but with very advanced technology. Like I cannot do it at home. I cannot make liquid oxygen at home. It requires fairly expensive and sophisticated, not very sophisticated, but some non-trivial instrumentation, which was not available at that time. So anyway, so he was the one who first established that liquids and gases are actually the same state of matter. And this boiling line, which gives you the temperature of boiling as a function of pressure, ends at one point. And that was sort of the start of the scientific studies of phase transitions. Okay, you can quibble about this, you can say Aristotle also knew something about phase transitions and so on and so forth. But it's a marker point, and it is perhaps fair to say that scientific study of phase transitions started with this. Okay, so here there is some caveats I would like to make. The first one is that despite the somewhat misleading title, my aim in this talk is not to give a history of the subject, but as I said, I just wanted to mark the 200th anniversary. I would like to list some milestones, the kinds of things that in 200 years. I will not describe any of these in great detail, but you can learn about them later, but I will list them, mention them, and of course I have to pick something that is very important and something is less important, and then make some comments about understanding today. And as I said, this talk is aimed at undergraduate students and known of Cagniet de la Tour. This portrait of Baron Charles Cagniet de la Tour is taken from an article by Bursch. This reference is given, and they say Cartier University University of Nîmes. From there they have borrowed this picture. But later I found that there is this guy Girolami, reference is given, says, as far as I know, there are no known portraits of Cagniet de la Tour, and images purported to be of him are actually of other people. So he's a baron, and even then people are not very sure about his picture. His work is very understood and established, but his picture is not there, and so okay, so this is the way history is. This is in Europe. In India, the history is even more uncertain, because we don't keep records very well. But anyway, so let's go on. So what experiment did he do? So this picture is actually this picture is a schematic representation of de la Tour's experiment. Actually, he did experiments over many years, and in the later years, the experiments were done sort of like this. The first experiments he did, he filled a high pressure vessel, which in those days was called Pepin's digester, which is like a pressure cooker. So there was some big vessel, you had to close it, and then it could generate very high pressures inside. And he filled it with some gas, and then you cannot see it, but he raised it to high temperature. He put a flint ball inside it, and then he slowly let the vessel cool, and he found that at high temperature, if you roll the vessel, there is not much sound, but if you go below some temperature, then you get a splashing sound, like it generates a liquid and a gas, and then when the ball crosses the liquid, there is a spark sound, splashing sound of some sort. And he could distinguish the sound and note that the sound appears only above some temperature and not below. And he correctly concluded that that is because the liquid and gas are the same thing above that temperature and not below. Okay, so this is the experiment. And so as I said, this picture is taken, you know, so you can take some stuff here, and this is mercury, and you can raise the thing and change the pressure and temperature of the vessel. This is a glass tube. So you can see what's happening. At high temperature, there is only one phase, which is called vapor. At lower temperatures, you get some liquid and some gas in the same instrument with the same composition. This experiment has to be done with these kinds of liquids like, you know, diethyl ether, because you have to be sure there is only one stuff inside. If you have air inside, then of course there will be air and liquid, and it's not the same thing. It's the same material. There is no air here. It's only the liquid, but here it is in this form, and here it is in that form. That's the difference. Okay, so he found that when the vessel is cooled enough, on rolling it, the splashing sound is produced, but not at higher temperatures. And this he explained, that at low temperatures there is a phase separation, liquid and vapor. I already told you. And this was the beginning of phase transitions. Very soon after, people like Faraday, actually it is not so soon after, but Faraday reported that he can liquefy other gases like nitrous oxide, cyanide, and ammonia, etc. And then Andrews in 1869, which is, you know, around 50 years later, made a detailed study of the effects of temperature on carbon dioxide, and clearly established the existence of critical point, and how does the pressure change with volume near this critical point, and this kind of stuff. And there is a famous equation called the van der Waals equation, which students read in the 12th grade. That was also published soon after these experiments, 1869 and 73, in the PhD thesis of the author, van der Waals. And for this work, of course, van der Waals later got the Nobel Prize as well. Okay, so these are the sort of milestones in the development of theory. One is this Cagniet-Dirac-Tuer, and then there is stuff with Faraday, and there is stuff with Andrews, and there is van der Waals. Okay. Okay, is this better? Okay, or yeah, okay, let me go on. Okay, so I just want to quote here from the concluding sentence of Andrews' paper. This ordinary gaseous and ordinary liquid states are only widely separated, the same conditions of matter. Nowadays we call it states of matter, and that may be made to pass into one another by gradation so gentle that passage shall nowhere present any interruption of continuity. It is a continuous transformation from solid to liquidity. Can you hear me better now? Okay, so you can go from the liquid to gaseous state continuously without any discontinuity ever appearing. Okay. And so at that time, it was a great realization that liquids and gases are not so different, they are the same thing. Now it's called the fluid state of matter. And the phase transition from solid to liquid is a transition from the one form of fluid to another form of fluid of the same material. Okay. So now these are the experiments, but in theoretical physics we usually have a theoretical framework, and in that theory you have to explain how phase transitions occur. So the basic theories of physics are quite well established, and so we just want to mention them here, that you can explain the existence of phase transitions in the framework of standard theoretical physics. We call it statistical physics. And let me just now discuss only stuff in thermal equilibrium. There are also phase transitions in non-equilibrium matter, like you can have a tube and it has some gas in it, which shine light on it, and sometimes it lasers and sometimes it doesn't laser. So depending on the power and all kinds of stuff. So there is a transition of the gas from a lasing state to a non-lasing state. It's a phase transition. but it's a phase transition in non-equilibrium matter. Okay, and we are not discussing it now because there is only a finite amount of time, and but it's an interesting thing, and you can study those transitions as well. So they, just there is also a transition from living to dead in cells and in living beings. That's also a phase transition, is from the living state to the dead state, and that's also a non-equilibrium phase transition. And I'm studying much simpler stuff here, and so we are dealing with stuff in thermal equilibrium and not with living processes. Okay, so this is just the theory of equilibrium phase transitions. It says, suppose you take a system of n molecules in a box, then you can have lots of configurations of these molecules. There is a thing called the Hamiltonian, or the energy of the system, and you can calculate this function called the partition function, which is some integral over phase space of this stuff. And if you calculate this thing, which is a complicated integral, multidimensional integral, but if you calculate it, then take the log and divide by n and take the limit, then you get free energy per unit, per particle in the system, and this free energy will show the behavior that you are looking for. So the partition function is an infinitely differentiable function of beta, because in the previous picture we showed that it's just exponential minus beta function. So it's a function which is infinitely differentiable, but the log of the partition function, and then you take the limit of large n, that need not be differentiable. And this is a picture of some system in which you change the value of n and see what happens to this free energy calculation. The details will not be important just now, but you see that if you make n bigger, then the graph becomes more and more sharper, and so for a bigger system you get sharper phase transition. At infinite n there is actually a jump in this graph, which is not present at infinite n. So the phase transitions are collective effects of interaction between constituent molecules. They don't occur when n is very small, 2 or 3. Formally you have to take n equal to infinity. In practice, if you take n equal to 1000, that's also quite good. Okay, so that is the general idea of phase transitions. Now, even the idea that the same theory can describe the solid, liquid and gaseous phases was not quite obvious in 1900. So, there used to be something called theory of solids, and there was also theory of gases and theory of liquids, and they were all distinct theories which looked very different in the beginning, and it was not very clear that you can actually describe all the 3 different states of matter or whatever other states there are in terms of only a finite, same Hamiltonian, same theory will describe both the solid and the liquid, and the fact that when you change temperature you go from solid to liquid. So Ising had shown that in one-dimensional Ising model there is no phase transition, and he had claimed wrongly that it doesn't occur in any dimension. But this paper was there and people were confused. But Kremers in 1 year around 1930 explained very clearly how you can have phase transitions in this thermodynamic limit, and this they did in some technical way in terms of some eigenvalues of transfer matrix becoming degenerate. I think there is a historical point that Kremers in 1 year worked out the transfer matrix for the Ising model very clearly. They wrote it down, but they couldn't diagonalize the matrix, which is what was needed to get the full answer. And so they didn't actually solve the Ising model, they just set up the problem in a more tractable way. And the solution of this model was actually in 2 dimensions, was actually done by Onsager. And so that is a famous work of 2-dimensional Ising model, which is sort of the prototype type of phase transitions. And so this is what we discuss next. So this is the prototypical model for understanding phase transitions. What is the model? You have a lattice like this. At each side there is a spin which takes, it's a magnetic spin, but it takes values up and down. Actually, sometimes the spins can take continuous values, but Ising studied this simple case. Other people before him also had studied it. Onsager studied this simple case. And so the Hamiltonian is just nearest neighbor coupling, they like to be parallel, and there is a string J. And given a configuration of spins, there is an energy. And given the energy, there is a probability that that configuration occurs, which is a function of temperature. And so Onsager actually calculated the free energy per site for all temperatures, and he showed that the model undergoes a phase transition from a low temperature phase in which there is a magnetization to a high temperature phase, there is no magnetization. So he showed that as you vary the temperature, at low temperature the system will show average magnetization which slowly decreases, but it becomes zero at a finite temperature and remains zero above. So this was an explicit exact calculation of a model problem which showed the phase transition and established once and for all that you can actually have phase transitions in statistical mechanics. Okay, I guess some phase transitions were discussed before by Bose-Einstein, but that was sort of some ideal guesses and nobody knew if there were any ideal guesses actually. And so, it was sort of, this was very important milestone in the study of phase transition. Okay, so now I come to this Lee-Yang theory of phase transition. So this is also very early, 1952. Onsager's work is 44. This is in 1952. They gave a theory, insightful description of how the non-smooth behavior of partition function occurs and how various quantities become big or small or singular near phase transition. And they discussed it in terms of there is a partition function which is a polynomial in the activity variable called Z, and then this polynomial has a lot of zeros and they change, and how they change, that they discuss the phase transition in terms of the movement of these zeros. So this is what is discussed here. Consider the grand partition function of molecules with a hard core and with long range interactions, and then they said this partition function is partition function of n multiplied by z to the power n, summation over all n. But since there is a finite volume and there is hard core, there are total number of particles is at most n max, and this is a finite polynomial. It's an nth max degree polynomial, then it has n max zeros in the complex plane. So then he said, well, let's look at the position of these zeros. When you take the log of this, wherever there was a zero, it becomes a singularity of the function. And so, this function, on taking the log, becomes singular. And so then you can ask what happens when you increase n. And the partition function is, when you increase n, then the number of zeros increases and they tend to fall onto some lines. So there are things called lines of zeros. So the partition function is analytically extended to the whole complex plane. The log of the partition function is potential due to unit charges placed at the zeros of omega, because in 2 dimensions so when we increase the volume of the box, n max increases, strength of charges decreases, and in the limit of large V, the zeros have a limiting continuous distribution, and Lee and Yang showed that in some cases there are lines of zeros with continuous line density. And when we change the temperature, the zeros move. If the zeros pinch in on the real axis, it gives singularities in the partition function. So what was realized very early is that this partition function never becomes zero on the real positive axis. So you can't really, since there is not, it's always positive, then you don't get any singularities on the positive axis. But in the thermodynamic limit, you can have zeros which are very close to the positive real axis and they show up as singularities. And this is a picture from the original paper of Lee and Yang. They said the zeros may look like this, and then you have in this region there is something, in this region there is something, but when you cross the line of zeros, then there is a singularity in the potential function, and so the free energy etc. will also show singularities of some sort. So it's very interesting that they showed this picture, because obviously in their mind they were thinking of 3 phases of matter, solid, liquid, gas, and this is putatively solid, liquid, gas, but turns out that this detail is not really correct, and they didn't ever claim this. This is just presumed to be what they were hoping to get. So this is sort of comment about our current understanding of this theory. While the general theory of Li and Yang is fully correct, it is now realized that in some cases the situation can be more complex, and one doesn't only have lines of zeros, but you can also have areas of zeros. There is an area in the complex Z plane where there is a finite density of zero per unit area, and this is the picture of some model or the other. The details don't matter. For this model, which is called hard hexagon model, you seem to get lines. There is some lines here and there is some lines here. But in this picture of hard squares, you seem to get, in this region there are lines, and here you seem to have a whole area in which zeros become more and more dense. And this is numerically determined with some 40 by 40 lattice, so 1600 zeros. Okay. So now I come to the scaling theory of critical phase transitions, which is an important topic on which large number of people have worked. So near the critical point, the liquid gas system shows very large correlated fluctuations of density, and exactly at the critical point, the correlation length is infinite in principle. In practice, in experiments, you cannot assure that the temperature is everywhere uniform and all these kinds of stuff, or the gravity is absent, which we didn't worry about. So, but in practice, you can easily get correlation lengths which are bigger than 10,000 angstroms, which is about 10,000 times the size of atoms. And so you can see the fact that light scatters differently and you get cloudy pictures, and so that signal of the fact that the correlation length is of the order of wavelength of light, which is very big. So many other physical quantities like specific heat and susceptibility show singularities at the critical point. So if you theoretically calculate it at the critical point, it is infinite. Near the critical point, it tends to infinity in some way. That tending to infinity is described by some kind of a singularity, and which are called critical exponents, denoted by alpha, beta, gamma, delta, etc. I will not give the definitions of these. But people got to worry a lot about the critical exponents, because the critical exponents show something which is called universality, which is the following: that you take different materials, you study their phase transition, they will occur at different temperature, and everything specific heat will be different. But if you look at the value of alpha for different liquids, it will be the same. If you look at the value of this exponent beta, it will be the same. So near the critical point, different materials show the same qualitative behavior. The behavior of different quantities behaves in the same way. So this is called universality, which makes, then I can have a theory which applies to all possible liquids or all possible transitions. And that is why people got interested in these critical phenomena. And then, in addition, these exponents are not all independent. They can be expressed in terms of 2 or 3 independent exponents. Okay? So, people can work out the fact that there is a relation between these quantities. You can check them. And so then, these exponents became interesting. And the scaling theory of critical phenomena was developed by Vidam, Kadanov, Fischer and others, culminating in the renormalization group picture developed by Wilson. So the basic idea of renormalization group theory is that the critical phenomena occur at large length scales, and they are material independent. So it is like the phase transitions people see in hydrodynamics. If you take a tube and you pass water through, at low pressure, there is a straight flow. At beyond some threshold pressure, there is a instability and the fluid becomes turbulent. Now, onset of turbulence, you study in some more detail, you will find that it's the independent of the details of what liquid you put in. You put in water or benzene, the liquids are different, the pressure head will be different, but the way the onset occurs is the same in different liquids, and it's independent of the size and shape of the tube you use. You can use rectangular tube, circular tube, bigger tube, smaller tube. They will all behave in the same way. So that is the understanding the theory of turbulence, the theory of this onset of turbulence is a matter of understanding hydrodynamics, which is given in Navier-Stokes equations. I cannot solve those equations directly very well, but if I could solve those equations, it will describe the turbulence of all liquids in pipe flow, right? So same way people said that if you try to develop a theory of liquids undergoing this liquid gas transition, there will be some theory which will be there, but if you look at the large length scales, much bigger than the size of atoms, then all the liquids will behave in the same way, and the onset of large specific heat, etc., will occur in the same way in different liquids. So that was the theory developed in I gave only a wordy picture, but it's developed by Wilson. The basic idea of renormalization theory is that this critical phenomena is governed by mutual non-linear interactions between long wavelength degrees of freedom. So these are the mouthful of words. Long wavelength degrees of freedom are called hydrodynamical modes, and non-linear interaction between them is whatever happens, they affect each other, of course. And if we can systematically integrate out the short wavelength degrees of freedom without changing the critical behavior, okay, and so this thinning out of degrees of freedom renormalizes the effective values of coupling between the unintegrated degrees of freedom. The critical point is the fixed point under this transformation, because when you have infinite correlation length and you change scale, it remains infinite. Linear analysis of changes near the critical point can determine the critical exponents. Okay, that is, I guess if you don't know this already, then it is hard to make sense of this in great detail. But I am providing some kind of a summary of a whole complicated theory, and so if you get some general picture of what's going on, that is all that is expected. And if you want to learn more, you will have to read the actual paper, so some more detailed account which will be 30 pages or whatever it is. Okay? So by now, the critical behavior of large number of systems is understood well. There are many exactly solved cases, especially in 2 dimensions. In 2 dimensions, there is some very fashionable stuff called conformal field theory, which can predict a lot of these exponents exactly and so on. In any case, in other cases, one can use different numerical techniques and you can get pretty reliable values of critical behavior. So I will not discuss this further here, but the studies of critical phenomena have been a dominant topic of research in statistical physics for last 50 years. So just as a sort of joke, but not really, I tell you a story. There was a student who joined us as talk. And so, he had already done a PhD somewhere or the other, and we were discussing what you can do further. And he said that, what can we do? You calculate some critical exponent or the other, that's all there is to do in statistical physics. But I was trying to explain to him, no, that is a very myopic view of the world. If you want to study phase transitions, you say, no, phase transition, I want to study them only near the critical point. And I only what is the behavior asymptotic near the critical point. That's a very narrow view of the world, right? So, but anyway, that is what has been happening. A lot of people work in phase transitions and they only calculate critical exponents. I think that is an interesting problem, but not the only interesting problem in the world. Okay. Okay, so now comes the question. In spite of large amount of work and much improved understanding, we can ask that, okay, we understand this. Is there something we don't understand? And I would say that we still do not have a model of particles with realistic interactions which is exactly solved and shows a solid to liquid to gas transition. We have models which show solid to liquid transition or liquid to gas transition. There is no single model gives you solid to liquid to gas transition, which can be solved exactly. Okay. So there are good zero order models of liquid to gas and solid to liquid, but not both. The models of molecules with Lennard-Jones type interactions does show these transitions. So the model which works is known. It is known that if you take molecules with Lennard-Jones type of interaction, it shows a solid phase and a liquid phase and a gas phase. But these results are known only in numerical simulation. There is no theory behind this yet. Okay, finding an analytically tractable model that shows solid liquid gas transition still remains a challenge. So in this context, it is good to remember that the problem we want to study is not just solid to liquid to gas, because the real world is more complicated than this. It doesn't always, solid doesn't always become liquid in one go. So there are mesophases. In meso means, so when you take a solid and you try to melt it, sometimes it melts into a liquid in one step, sometimes it goes into several steps. And so the melting transition is from a crystalline phase, shows broken translational and rotational invariance, to an isotropic liquid. The solid has a, in all directions it doesn't look the same, but liquid looks the same. And so these symmetries are broken. And for non-spherical molecules, it often happens in stages. And there are mesophases or liquid crystals and orientationally disordered solids called plastic crystals. So what are these things? So liquid crystals are well known. They are actually show many possible phases, nematic, smectic A, smectic C. There are many other names. In these cases, what happens is that the orientational symmetry, the things start out solid, then they become translationally invariant, but the orientational symmetry is still broken. So one of the two symmetries is there, the other is not there. So that is, it's a half, in some ways it looks like a liquid, in other ways it is broken symmetry, it looks like a solid. And so they are called middle phases, and there are many such known, and of course they are technologically very important and studied a lot. In contrast, plastic crystals are the opposite. What happens here is that the crystalline lattice remains, but the orientational degrees become restored. So you have things like nitrogen gas, as common as that, and it forms a solid, but the nitrogen molecule is an asymmetric molecule, it's rod-like, and it rotates. And so in the solid, it doesn't rotate freely. So if you look at solid, it will have different molecules of nitrogen roughly in a crystalline shape, but there is no unit cell because all the molecules have different orientations. But if you heat it further, then the solid is broken. So the transition occurs in stages, and so they are called plastic crystals because they are crystalline, but they are very soft. They were initially called plastic crystals. The modern name is orientationally disordered solids. Okay, orientationally disordered solids. Okay, so here is a picture of liquid crystals. So here is a crystal, and when you heat it up, it goes into something like this. There may be layers. So the layers can slide past each other, but within layer there is sort of still a crystalline order. Or they can be, different types of layering. Or they can be like this, where the orientationally they are in some direction, but there is no layering even. So that's called a nematic liquid. And then there is an isotropic liquid in which there is neither orientational asymmetry nor there is a translational asymmetry. So these are the multiple phase transitions in some phenylene ester. Figure is taken from some reference is given here. So now I discuss these orientationally disordered solids, which were discussed a lot in 1930. And they are discussed still in chemistry, but not so much in physics. So many molecular solids on freezing first form a phase where centers of molecule form a lattice, but the orientationals are random. And they were studied initially by Timmermans in 1930. He worked for some 30 years, and After that, a lot of other people have done this. On increasing temperature, there are multiple points where there is a jump in density or in specific heat, and there are transitions. So here is a picture, just one picture. So here is a temperature, this is specific heat, there is a liquid, and there is a solid 1, solid 2, solid 3. There are 3 solid phases, and this is the normal crystalline solid, and this is the normal liquid, and in between there are these 2 other phases, which are mesophases, middle. They are neither fully liquid, neither fully solid. And so if I have a theory of solid to liquid transition, I should understand this or explain these as well. When do they occur, when they don't occur, why they don't occur. And somehow these have not been studied much in physics literature because they are not critical phenomena, these are first order transitions. Okay, so then I just want to take a few minutes to describe a model of multiple phase transitions in plastic solids which we studied recently. So it's an opportunity for me to advertise some work, also to give you a, I'm doing this, but I'm doing this because I would like you to also make a feeling that there is still some work which can be done in this area. This may not be the greatest work in the subject, but I am giving it as an example of some ongoing work which people do in this general field. Okay, so this work is done with Philippe Sadhu, Julian Klemser, and Sushant Saryal. This person is at TIFR, he is at École Normale Paris, and Sushant actually now in Germany, and Sushant Saryal is just finished PhD at IISER Pune. So we consider a lattice model. So you take a lattice and you put some asymmetrical solids on this. So we took actually something like just a disk which is symmetrical, but you put a pivot point at a non-central position, and you put the pivot at the lattice point, and then the thing can rotate, and when it rotates, you can tell different orientation. So that's all there is. There is a lattice you can see, and there are these disks. But the centers of the disks are not at the lattice position, the pivot positions are somewhere else. Okay? And then as you vary the lattice spacing, this system undergoes phase transitions, more than one. And you can, so it shows multiple phase transitions, and at that level they are, if you compress these molecular solids, you see multiple phase transitions. So at this level of description, these are similar qualitative behavior. So in this model, we find multiple phase transitions as the ratio of particle size to lattice constant is varied. The distribution function of orientations as a function of singular, as a function of direction has many singular points, and these points change as the spacing is changed, and the qualitative feature of the distribution functions can be exactly calculated in some simple cases. So here there is a picture of the different kinds of angular distribution function. At some spacings you will see pictures like this where there is some dip and there is a flat part. Then if you change the spacing, the flat part is not there. The flat part also becomes a dip. There is a big dip and a small dip, and then these dips merge into fewer dips. These are 12 and these are only 6 in number, and then you get similar picture to this, except that the bigger dips and smaller dips have exchanged position. But all these qualitative features you can explain. The position of the singular points also changes with x, and that also can be calculated exactly within the model. Anyway, so the final summary is that we have come a long way following the pioneering work of Carnier de la Tour, but the theoretical understanding of things like the solid liquid gas transition is still not fully satisfactory. Okay? And more work on analytically tractable models of first order transitions and mesophases is desirable. And that is where I will stop. And I will be, I know that there is some time left, and I am happy to take some questions if you have any.
Thank you, Professor Dhar, for the inspiring lecture. So, is there any questions from the audience? Yeah, Ujjal.
You will have to speak louder. So, I actually don't know this. But see, you have to realize that at that time, the experiments were done in people in Royal Society. This was reported in the Royal Society at that time. They would tell the experiment that they took some rhino horns and they put it on table and they made ants go around it and what happens. So there was a general interest in investigating nature and see if something interesting happens. And I think at that time, Cagniet de la Tour was not a very big man, but he reported this stuff. And when he reported this, then I think whoever was the president of the Royal Society said that this looks like a very interesting result. You have to mention, you have to report it right away. So in the annual meeting of the Royal Society, which was occurring 3 days later or some such thing, this work was accepted for oral presentation. And so people realized the importance of the observation as soon as more or less it was reported, and it was appreciated by large number of people, including Faraday, who continued this kind of work later himself, and so on. So I don't know why he did this, but seems to have been an ingenious person with an inquisitive mind. And there is no reason why, some such thing cannot happen again today.
Any other questions? Yeah, Samrat.
You wait for the mic.
No, that's not. It's not.
Yeah, so it's a beautiful talk. So I was just wondering, when you talked about this tour experiment, did anybody recognize dew formation as a phase transition even before tour? Like, because dew formation is indeed sort of a day-to-day experience of phase transition.
No, so people have certainly knew that the dew is made up of water and it comes in from the air. But whether you call it phase transition or not is more a matter of the word phase being already popular or known I think this notion of phase was not very clear. And liquids were treated as something, as I said, and the gases were treated as something else. And the fact that they are made up of the same matter was not fully clear at that time, not fully appreciated. So to that degree, I think the fact that dew is made up of water would be known, but calling it a phase transition may not be so obvious.
Okay. Yeah,
Yes.
PG.
So this is more of a comment than a question. In the eye lens of every vertebrate, there are cells that are filled with proteins at such high concentrations that the state is a glossy state.
Sorry?
A glossy state with short-range order, and that results in the destructive interference of scattered wavelets of light, and that results in transparency.
Yes.
Initially, it was thought that it's a crystalline state, and so the proteins were called crystallines, but then it was discovered that it's a glossy state as late as, I think, 1972. So there's a case of phase transition that happens when you turn about 50 or 60 or 70 years of age, when this glass turns from a semi-liquid to solid,
Yes.
when cataract develops in the eye. So Samrat was talking about a common everyday phenomenon that can be called a phase transition, and you said that the word phase might not have been used at that time. So another such similar incidence is the formation of a cataract.
So the fact that you take something like glass as a liquid and you cool it, you get a phase which is called the glassy phase, and glassy phase is not crystalline. It's certainly well known for 2000 years or so, right? People knew how to make glass around that time. But the understanding of the glassy phase is not so easy, and it was not there then, and it is perhaps not fully there even now.
Okay, Tripta?
Thank you for the talk, sir. Sir, so in one of the slides you showed, can you go back to that slide? The last one with, just explaining the different stages of solids before it actually goes to, and then you showed us some graphs after this where you show different dips.
This one?
Yeah, so this model that you explained.
Yeah.
So if I understood it correctly, you said that you are varying the lattice spacing. So this is a short length.
So changing the lattice spacing is changing the density.
Yeah, so but at some point you mentioned that when we do the renormalization group theory, then it is about looking, all the short length scales are actually not playing, what is happening at the short length doesn't play any role. It's more or less at the large.
So the renormalization group picture works well when there is an infinite correlation length. If there is only a finite correlation length, it has some predictions but not very strong. So for first order transitions, the renormalization group picture is not much used.
So these are all first order phase transitions.
These are typically first order. In this particular case, you actually get singularities in some scattering function or something, but you don't get always first order jumps in density. By hand, the density is varied by continuously. Okay? But, this is a toy model of something or the other. We were just happy that you can get 3 different phases or 5 different phase transitions from solid to liquid in between, right? Nothing more is expected or obtained.
Thank you.
Okay, so one more question, the last one, Pata.
Okay, so actually then, so let me go to the next picture. Here, so this is done on a triangular lattice, so it has the symmetry of the triangle. So there are 6 prominent peaks which refers to the fact, and they are symmetrical about after 60 degrees you get the same picture again. So right now that is the origin of that, that 6-fold symmetry of the lattice gives rise to 6-fold symmetry in this distribution function.
Okay. Thank you. So please join me in thanking Professor Dhar for his wonderful lecture.
Thank you.
Now I request the Director, Professor Gauri Shankar, to present a memento to Professor Dhar on behalf of the Institute. Professor Gauri Shankar. Thank you very much. So I request both of you to stay here. Yeah, please. So now we move on to. Sorry. So now we move on to the prize distribution. This year we have announced an open competition among the faculty, research scholars and undergraduate students for designing the cover page of the annual report for the year 2021 to 22. And we have received overwhelming responses from the faculty and students. And a committee evaluated the designs and selected 3 best designs for the annual report. So I request, I request Rachna Chava to be on the stage, please. Yeah, okay. All right. So the first prize, that is the 20,000 rupees cash prize, goes to Mr. Manohar, a second-year BSMS student of IISER Mohali. Congratulations to Manav. Thank you. The second prize, that is 10,000 rupees cash prize, goes to Dr. Tripta Bhatia, faculty in the Department of Physical Sciences, IISER Mohali. Congratulations, Tripta. Thank you. And the third prize, that is 5,000 rupees cash prize, goes to Dr. Shantanu Paul, faculty in the Department of Chemical Sciences, IISER Mohali. Thank you. Now I request Dr. Vishaki, the librarian, and Dr. Rajesh Ramachandran and Mr. Vineet Gaurav to come to the stage, please, to announce the Best User of the Library Award. Thank you.
Good evening, one and all. To encourage reading habits in library, the Institute has introduced the Best User of Library Award from 2019. And this year, there was a tie between James Watt from 2019 batch and Shreyas Jain from MS-20 batch. So, James Watt got last year in 2020 batch also. In 2020, he was the Best User of Library Award he has received. So jury by Dr. Rajesh Ramachandran and Vineet and me decided that, recommended that because he is maintaining constantly the same reading habits and good decorum in library, so director has kindly approved. Now we want to honor him with appreciation certificate. I request James Watt and Commander S, please. So this year, the best user of library award goes to Mr. Shreyas Jain from 20 batch, MS 20. I request Mr. Shreyas to be on dais, please.
Thank you very much. So now I invite Dr. Rachna Chaba to give vote of thanks, please.